Basic radar cross-section calculation in Feko starts by defining the target for the RCS calculations in CAD Feko. The target can be constructed either using CAD Feko's built-in geometry construction tools or by importing from one of many supported CAD or mesh formats. For this demonstration, we will use an IGES file that contains the geometry of a simple object that we would like to calculate the radar cross-section of. Once the geometry has been defined, we specify the frequency or frequencies at which we would like to perform the radar cross-section calculation. In this demonstration, we will use 300 MHz. Next, we need to specify the directions from which the object should be illuminated. This is configured by selecting a plane wave excitation. For this demonstration, we would like to illuminate the object in the theta equals 90 plane by varying phi from 0 to 45 degrees in 1 degree increments. We would also like to illuminate the object both in vertical and horizontal polarizations. Now we need to specify the directions from which we would like to observe the target. In the radar cross-section calculation, for monostatic RCS, we observe from the same direction as the incident illumination. Now we are ready to mesh the model in preparation for simulation. After meshing, we can visualize the mesh, and if needed, we can choose specific solution parameters for the calculation. For this demonstration, we will use the MLFMM to accelerate the default method of moments solution. The model is saved, and we can run the solver. The simulation for the simple object is very fast, but comprises many radar cross-section calculations, one for each combination of frequency and incident and observation direction. If there are specific materials, properties, or simulation settings that we would like to make, we can do these easily in CAD Feko. For this demonstration, we would like to use ray-launching geometric optics solution. Unlike the MLFMM, this method is applied to selected parts of the model. We select the faces of our object and set RLGO in the Solutions tab. Feko has many different solution options which may be used. In this case, MLFMM is not compatible with ray-launching geometrical optics, so we can switch that off, and we can confirm that the RLGO settings are as we would like them to be. We are now ready to remesh our target object. Due to the changes in the solver approach that we have chosen, our radar object is meshed in a different way. In this case, larger curvilinear elements are used. Once the radar cross-section simulation has been completed, we can view the calculated output by launching the Feko post-processing interface, PostFeko. In PostFeko, we can add the full-fed results that we've computed to a 2D or 3D plot for visualization and further analysis. For this demonstration, we'll view our results on a polar graph, select the RCS quantity in dB. For more advanced RCS simulations, the basic workflow is the same, but of course the geometry setup and post-processing may be more complex. Feko provides various tools to help with this, including flexible and customizable scripts that can be used to configure just about anything. In order to set up a simulation that will enable advanced inverse synthetic aperture radar post-processing, for example, a script is used to calculate variables that can then in turn be used to set up the frequency, excitation, and request definitions. We simply use these variables in the frequency, excitation, and request configurations, and we are ready for simulation. For this demonstration, there are more frequencies and observation points, and therefore many more calculation steps to complete. Once the simulation is completed, however, we can launch the post-processing interface. Here, we can again use highly flexible scripting and also built-in tools to perform advanced processing. For this demonstration, we would like to view the ISO of our simple object. The ISO processing tool allows us to make various choices based on the simulation data available as well as the viewing range to be considered. The calculated inverse synthetic aperture radar image for the chosen processing and angular range shown here on a decibel scale in a three-dimensional view, appears to be more complex than we may have anticipated. If we overlay the target with this ISO image and take a closer look at it, we can see that the radar processing highlights details of the object that we were not aware of. This simple and friendly target is in fact composed of different materials, giving it a unique and identifiable radar signature.